Okay. Hi, this is Abe. Today I'm going to talk to you about derivatives. Now, I assure you, we're not really getting into calculus. It's more like algebra, like the picture suggests. There's no magic involved. Now, we know about gradient, right? Gradient's really simple. You've got a straight line going on, and you're like, okay, rise and run, and you're like, gradient is rise over run, right? We all know that. Really, really simple. But derivatives talks about something different. It says that if I have a curved line and I'm interested in the gradient at a particular point, how do I go about finding it? Notice that on this line, the gradient keeps changing. Like, at this point, it's that, right? But at this point, the gradient is that. They're different. They happen to be different. And so the gradient keeps changing. So how do you find a gradient just at that particular point? Let me draw this line in again. Now the gradient, let's say I'm interested in finding the gradient at the point A, right? The gradient at the point A is going to be something like that green line. That green line, what I've drawn is a tangent, where it's a line that just touches the point A, and at exactly this point, that it represents the gradient at exactly that point. So yeah. Now, how do I go about doing this? That's really the question of what we're trying to look at today. So, I'm going to tell you something that actually there's no magic involved. What you're going to do is you're going to do exactly what you've always done with gradients. You're going to find a second point, you're going to draw a triangle, and you're going to do rise over run. Okay? This is your second point here. I'm going to call this A plus H. You'll see why in a moment. So the x-coordinate of this point is A. The x-coordinate of this point is A plus H. Okay. Now our line is called f of x. And so the y-coordinate of point A is f of A. And the y-coordinate of this second point, A plus H, is f of A plus H. Simple, right? Simple, very simple. Now, watch as I replicate the triangle on the left. This is my new triangle. So, I've got a line running from A to A plus H. This line also has a rise and a run, right? And with this run, or with this line, I'm going to calculate the gradient at the point A. Okay, so looking at this triangle, you'll see that the rise here, the rise is equal to, what is it, top value minus the bottom value, right? F of A plus H minus F of A. What about the run? The run is equal to the right value minus the left value. So, A plus H minus A, which is just H. Okay, now I'm going to introduce to you some notation here. Notation runs like this. F dash A. This means the derivative of the function x, the function f, at point A. So that's what I want, right? The derivative means the gradient. So f dash a means the derivative of function x, function f, at the point A. And I've established I want to estimate it with this red triangle that I've drawn on this previous graph. Sorry, wrong color. There, better. So because it's an estimate, let me rub this out. Because it's an estimate, I want to just do that. Now we know that it is roughly equal to rise over run, which we saw over there as f of a plus h minus f of a over h, right? Okay, here comes the intellectual leap. Really simple. The idea here is that you see that red line, this red line, the gradient of that line is different to the gradient of this line. Whoop. Right? But how can you make it more the same? You can actually improve it. You can improve it by reducing h. Example here. Draw this in black. Let's pretend that instead of having our second point way out here, instead of having it out here, let's have it here. Do you see it? So our resulting estimate is going to be like that. Yeah. Do you see that the black line is a better approximation than the red line? So a key bit of learning here is that our estimate gets better as h gets smaller. Okay? Cool. So now, I have a question. What happens as h becomes really, really small? If h becomes really, really small, your thing is going to become very, very, very accurate. So in other words, what I'm asking is, what happens if I make my line, if I make my second point not here, not here, but right there? If I were to do that, then my second point would really just have the proper gradient. The proper gradient of the line. Almost. Pretty much. Right? I can get as close as I like to the correct gradient. And that's the whole idea of derivatives and calculus. So, to put this idea into concrete, I'm going to use something that you've seen before. Limits. So, notice here that I've used approximately equals, right? If I use limits, I can actually not use approximately equals. I could actually say this: f dash a equals the limit as h approaches 0 of f of a plus h minus f of a over h. This is a formula you have seen before, I certainly hope. Ta-da. So, the idea here is that h can get as close to 0 as possible, but it can't actually get to 0. And the reason it can't get to 0 is because, well, you've got rise over run, right? If your h is equal to 0, then you've got no equation. So h is not allowed to be 0, but h can be really small, like 0.00001. That's perfectly fine. So this essentially is the idea of derivatives, and this formula I've sort of circled over here is the derivative. If you want to change it, it's just f dash of x. This is usually you'd use x, limit h going to 0, f of x plus h minus f of x over h, and that's it. So we'll do an example on this in a different video, but for now, that's derivatives. See, no magic involved. Very simple. Thank you very much. Bye.